Welcome to today's explainer. We're so used to the everyday magic of just flipping a light switch. But today, we're actually going to bypass all that and dig straight into the physical engines of electricity. We're going to demystify its hidden powers, everything from those invisible magnetic fields to modern chemical storage. It's going to be a fun ride. Okay, let's take a quick look at our roadmap for today. We'll be unpacking some major mysteries: electricity's magnetic secret, building an electromagnet, the heating effect, the birth of batteries, and finally, modern power storage. Let's get right into it. All right, Section 1, electricity's magnetic secret. And spoiler alert, this was actually an accidental discovery. Picture the scene. It's Denmark, 1820. Professor Hans Christian Ørsted is just giving a standard run-of-the-mill university demonstration when he makes this totally startling observation. He noticed that a nearby compass needle unexpectedly twitched, just a little jump, whenever he opened or closed an electrical circuit on his desk. It was a tiny movement, sure, but honestly, it was completely earth-shattering. What's really wild here is just how simple his setup was. Literally, just a wire connected to a power source sitting next to a regular old magnetic compass. Ørsted's experiments with this super straightforward arrangement proved, definitively, that electricity and magnetism are intimately linked. Before this, people thought they were entirely separate forces. Crazy, right? So this brings us to a really crucial phenomenon, the magnetic effect of electric current. Basically, when an electric current flows through a conductor, it actually produces a magnetic field around it. An everyday current-carrying wire is generating an invisible magnetic field. But, and here's the catch, that field completely disappears the precise moment the current stops flowing. Moving on to Section 2. Building an electromagnet, or as I like to call it, harnessing the invisible. Let's see how we can actually control this. Building your own electromagnet is elegantly simple. Step 1, you just take a flexible insulated wire. Step 2, tightly wind about 50 turns around an iron core, like a standard nail. And Step 3, connect the ends to an electric cell. Just like that, boom, you've created an electromagnet. It behaves just like a regular magnet and can pick up iron paper clips. Disconnect the wire and, well, the magnetic field vanishes and they fall right back down. Now, you might be wondering, how on earth do we lift something heavier than a paperclip? Well, you've got a few options to power this up. To make an electromagnet stronger, you can increase the number of turns in the wire coil, or simply pump up the electric current by adding more battery cells. Using an iron core gives you the maximum practical strength. And here's a totally fascinating twist. You can actually flip the north and south poles simply by reversing the direction of the electric current. It's like having a programmable magnet. Let's connect this back to the real world for a second. Think about those massive factory cranes and scrap yards. The heavy-duty lifting electromagnets suspended from those cranes use this exact same principle to sort and move heavy steel. They pick up literal tons of metal with a huge surge of electricity and then drop it exactly where they want it simply by switching the current off. It gives us total, on-demand control over magnetism, a real game-changer for industry. All right, Section 3, the heating effect, glowing wires and morning coffee. Let's look at electricity's second major trick. As you can see, this beautifully illustrates the heating effect in action right inside our own homes. Room heaters, electric stoves, kettles, irons, your hairdryer, every single one of these appliances relies on this exact same physics principle to function. To understand how those everyday gadgets actually work, we have to talk about resistance. Resistance is simply the opposition a conductor offers to the flow of electric current. Think of it kind of like electrical friction. As the current fights its way through this opposition, that friction converts electrical energy into heat energy. And that is the very heat we use to boil our morning water or press the wrinkles out of our shirts. Now, the material you use for this matters immensely. Comparing nichrome to copper, for instance, reveals completely different behaviors. A nichrome wire offers much higher resistance than a similarly sized copper wire, meaning it gets incredibly hot. It's literally perfect for a toaster. Copper, on the other hand, offers low resistance, which is ideal for safely transmitting power through the walls of your house. And this highlights an absolutely crucial safety rule. Pushing too much current through low-resistance wires creates unwanted heat. Actually, scratch that. It creates dangerous heat, which is exactly why overloaded circuits can melt or even start fires. Okay, Section 4, the birth of batteries. So where exactly does all this juice come from in the first place? This takes us back to a really fascinating scientific debate from the late 1700s between Luigi Galvani and Alessandro Volta.
Galvani noticed that a dead frog's leg kicked when touched with two different metals, and he theorized this was animal electricity at play. Volta completely disagreed. He argued for metal combination, proving the electricity actually came from combining two different metals. To prove his point, Volta replaced the frog entirely with salt water-soaked paper, and it still generated a current. It proved that the metals and the liquid generated the power, not the frog itself. Poor frog, right?
So Volta's brilliant discovery led directly to the very first battery, the voltaic cell. The principle is so delightfully simple, you can literally replicate it in your kitchen. Notice how everyday lemons can act as the liquid electrolyte, working right alongside copper strips and iron nails that serve as the metal electrodes. Connecting them with wire sparks a chemical reaction, generating just enough current to light up a small LED. It's practically science magic. Finally, Section 5, Modern Power Storage, from dry cells to the future. Let's see how this evolved. Now, what's really interesting here is the stark contrast between these two types of storage. On the left, we've got a traditional single-use dry cell battery. It uses a zinc container, a carbon rod, and a paste-like electrolyte. It's super convenient, but sadly, it's totally dead once the chemicals deplete. On the right, though, we have modern rechargeable batteries, like the ones powering our laptops or electric vehicles. These can actually reverse their internal chemical process when you plug them in. This allows them to be reused hundreds of times, which saves us money and massively reduces environmental waste. But what powers the vast majority of these modern devices? Well, that's the lithium-ion reality. While it's today's most common rechargeable engine, it relies heavily on very specific metals, namely lithium and cobalt. Because these critical materials are mined and processed in limited geographic areas, there's a massive, high-stakes global race underway right now to secure supplies, recycle old batteries, and aggressively develop entirely new storage technologies. And that leaves us with a really vital question to ponder. Are solid-state batteries the next big leap for our planet? Scientists are urgently working to replace those liquid electrolytes with solid materials. If they're successful, these future batteries would be vastly safer, charge significantly faster, and last much, much longer. As the world desperately moves toward eco-friendly power, will this chemical breakthrough finally give us the sustainable electrical storage we actually need to power the future? Something to think about. Thanks so much for exploring the hidden powers of electricity with me today.